You're scrolling through your phone and you see it, right? Another headline about some breakthrough diet, a new wonder drug, or a study that links your morning coffee to, well, to just about anything. We are absolutely flooded with this stuff every single day. But how do we know what to actually believe? How do scientists sort out a real medical advance from just, random noise? That's the million-dollar question, isn't it? When you hear a clinical trial says a new treatment works, how can they be so sure? How do they know it wasn't just a lucky coincidence? Well, the answer isn't magic. It's actually a really powerful and fascinating field of science. And the hero of our story today is biostatistics. Seriously, think of it as the detective work behind all of medicine. It gives us the tools to take all of this messy, complicated health data and find the real truth that's hidden inside. It's how we go from just a hunch to a conclusion that we can actually trust with our health. So, how do we make that journey? How do we get from the hype of a flashy headline to the genuine hope of a new treatment? Well, it all starts with learning the fundamental language of the data itself. You see, at its heart, this all begins with data. And just like any language you might learn, data has its own grammar, its own vocabulary. And the two most basic parts of speech in this language are what scientists call qualitative and quantitative data. It's a really simple but incredibly powerful distinction. On one hand, you've got qualitative data. This stuff sorts things into groups. It answers the question, what kind? On the other hand, you have quantitative data. This stuff measures things. It answers how much or how many. Pretty much every single piece of health information you can think of falls into one of these two buckets. Let's make this real. Your blood type, for example, is a category. You're either in group A, B, AB, or O. That's qualitative. Your age, though, that's a number. You can measure it, you can do math with it. That makes it quantitative. Same idea with a drug brand. That's qualitative. But the time it takes for that drug to work, measured in minutes, that's quantitative. See the difference? Okay, so researchers run a study and they collect all this data. And what they get at first is, well, it's basically just a giant messy spreadsheet, a wall of numbers and categories. The very first job of a biostatistician is to bring some order to that chaos, to clean it up and make it something a human can actually understand. And this whole process is called descriptive statistics. The name kind of says it all, right? It's about describing the data you have right in front of you. This is the toolbox you use to tidy up that spreadsheet and start to see its most basic features. So, for instance, take a look at this table. It's showing the blood types of 50 patients. All the information is there, it's totally accurate. But your brain has to do a little work to figure out what's going on. Which group is the biggest? Which is the smallest? You gotta scan the numbers, right? It takes a second. We can do way better than that. I mean, at the end of the day, our brains are just wired to process images. When it comes to understanding data fast, nothing, and I mean nothing, beats a good picture. And boom, by turning that table into a simple bar chart, the story just jumps right out at you. The B bar is obviously the tallest. It's the most common blood type in this group. The AB bar is the shortest. You don't have to read or calculate anything. You can just see the results instantly. Or we could use something like a donut chart. This is fantastic for showing proportions, how each piece relates to the whole pie. You can immediately get a feel for the fact that type B makes up over a third of the entire group. It's all about telling a clear, immediate story with the numbers. Now, besides visuals, we often want just one single number to summarize our data. We want to find the center, or the most typical value, and biostatisticians have three main ways to do this: the mean, the median, and the mode. First up is the mean. You probably know this one as the good old average. You just add everything up and divide by how many things you have. It's simple, which is great, but it has one major weakness. It gets totally thrown off by extreme values or outliers. So if you're studying recovery times and just one patient recovers almost instantly, they could pull the whole average down and make a treatment look way more effective than it usually is. And that is exactly why we have the median. If you line up all your data points from smallest to largest, the median is the one smack dab in the middle. That one super fast recovery time, it doesn't affect the middle value at all. So the median often gives a much more realistic picture of the typical outcome. And finally, there's the mode. This one's the easiest. It's just the value that shows up most often. Now, here's the cool thing about the mode. You can't calculate the average blood type, right? But you can find the mode. In our example from before, the modal blood type, The one that appeared most often was B. Okay, so describing the data we already have is incredibly useful. But this next part, this is where the real power, the true magic of biostatistics comes in. It's using what we know about a small group of people to make a really smart, educated guess about everyone. Welcome to the world of inferential statistics. This is how a clinical trial with just a few thousand patients can lead to a drug being approved for millions of people. It's the science of making that reliable leap from the known to the unknown. Think of it like this. You're making a giant pot of soup. You don't need to eat the entire thing to know if it means more salt, right? You just taste one spoonful, that's your sample, to make a solid conclusion about the whole pot. That's your population. It's the exact same idea. So how on earth can this guess be reliable? It works because of this amazing, predictable pattern that we find all over nature, often called the normal distribution, or the bell curve. Imagine we're measuring something like height. Most people will be kind of close to the average height. A standard deviation is just a way to measure the typical spread around that average. And for a lot of things, about 68% of people will fall within one of those standard steps of the average. Now, if we take two standard steps out from the middle, we now capture about 95% of the population. And this 95% confidence level, it is a cornerstone of medical research. When a study says a result is statistically significant, what they're often saying is there's less than a 5% chance they'd see this result if the drug actually did nothing at all. And if we go three standard steps out, we've included 99.7% of pretty much everyone, the whole population, almost. Anybody outside of this range is a true outlier. This powerful rule is what allows scientists to figure out if a result from their study is just normal random variation, or if it's something truly exceptional and really, really important. So let's bring this all back home. Remember that headline on your phone we talked about at the very beginning? Well, all of these concepts, from organizing data into charts, to calculating a median, to making a statistical guess, all of it, these are the building blocks that lead to that news story. And that's why this all matters. Biostatistics is the rigorous, step-by-step process that tells us if a new treatment really works, if a public health program is actually saving lives, or if a health risk is real. It's the invisible engine that powers all of modern medicine. It gives us the tools to separate evidence from wishful thinking and fact from fiction. So the real question is, in a world that's so full of noise, are we taking the time to listen to what the data is actually telling us?